Greg, listen, there's tons of waves. No, I'm not kidding. There are awesome waves. You gotta get down here. I'm telling you. Hey, Rochelle.
Where's the waves at?
What are you talking about?
I don't see any waves.
Oh, come on. I mean, there's sound waves, there's light waves, there's radio waves, and there's some X-rays, gamma rays. I mean, right now, Rochelle, we're surrounded by billions and billions of waves.
Can't ride any of them.
Well, no, but they're waves.
Sports figures. Put your brain in the game.
If I were to throw a ball at these cans, no big deal, right? I gave the ball some energy, the energy traveled across the sand to the cans, and they fell down. But what if I were to do this? Oh yeah! Pretty cool, huh? Well, that's how waves work. Waves transfer energy from one place to another without moving matter. You see, ocean waves and sound waves are moving energy. That's why when you're at the beach, you're not really surfing water. You're surfing energy. You should call this thing an energy board. Hey, listen, can I call you back? Okay, all right, bye. You know, waves are around us all the time. There's sound waves, there's electromagnetic waves like radio waves, there's microwaves, there's light waves. You know, even your cell phone works because of waves. Now, luckily for us, most waves aren't visible to the naked eye. That's why looking at ocean waves can help us understand waves. It's one of the few places you can actually see waves in action. And of course, ocean waves are great for surfing. Now, to help us out today, we've got Rochelle Ballard. Now, Rochelle has been on the World Championship Tour for 11 years. She also holds the record for scoring 2 perfect 10s in a single heat and has been voted the most popular surfer for the last 3 years. She also hosts her own camp, the Rochelle Ballard Surf Camp in Hawaii, and this year is doing it on both coasts. And she was featured in the movie Blue Crush. So I'd say she knows a thing or two about big waves. So, Rochelle, you're into ocean waves, right?
Right.
So, what can the ocean tell us about other kinds of waves?
Well, ocean waves actually have the same basic properties as all the other waves out there. It's just that you can see ocean waves.
Okay, cool. Let's start with the basics. Where do waves come from?
It starts off by a storm out at sea, and the wind actually kicks up and creates a wave.
So, if we're talking about waves as transferring energy, let's say, it's the energy from the wind is transferred into the wave, right?
Right. So when there's a big storm out at sea, it's creating a lot of energy, so I'm heading to the beach.
Unlike ocean waves, sound waves are caused by vibrations. Vibrations set up a disturbance in the medium. Like when I give energy to this tuning fork, it vibrates and disturbs the air around it. That disturbance travels out through the medium, the air, as waves. To understand how waves work, we start here with the pendulum. A pendulum swings back and forth, right? Like a grandfather clock. Back and forth, back and forth. The time it takes for the pendulum to complete one back and forth is called a period. Now here's something really cool. What happens if we lengthen the arm of the pendulum?
Lengthens the time of the period. It slows down.
Right, Galileo figured that one out. Now let's say I pull out the plug, start to let the sand funnel out. What happens?
It goes back and forth in the same spot, and we get a line.
Yes, but what if I start to move the sand?
We get a wavy line.
Ah, what's that called?
It's called a sine curve, or a sine wave.
Sort of looks like waves in the water. See, the sine curve is the shape of the wave. Now, there's 2 elements that make up a wave. The crest is the top of the wave, and the trough is the low valley part. You need both to make up a wave. the crest, and the trough. So how high was that wave?
That wave had an amplitude of about 3 meters. Amplitude is the height of the wave.
No, wait, 3 meters. It seemed much higher than that, though.
Well, you're looking at 3 meters of the crest of the wave, and you're looking at 3 meters of the trough of the wave, when actually you're taking your reading from where the flat water would be.
To measure the height of a wave, its amplitude, we have to draw a line down the center of the wave.
The distance from the center line to the crest is the wave's amplitude, how high it is.
And the trough is also the same distance from the center line.
So, Rochelle, what's the other way that waves are measured?
Well, besides the amplitude, the wave height,
Right.
you actually have the wavelength.
Wavelength. Okay, how do we measure that?
The wavelength is measured from crest to crest. It's the distance between those.
If you measure these waves from crest to crest, I'd say they're about a good 10 meters apart. FM radio waves look like this, and their wavelengths are measured in meters. From crest to crest, it might be about 3 meters. AM radio waves have a wavelength of about 200 meters. That's longer than 2 football fields.
Besides amplitude and wavelength, there's another way we measure waves in time.
Right, how frequently the wave comes in, we call that the wave's frequency. When you tune in a radio station, you're tuning to the frequency of that station's radio waves. Now, if you've ever looked closely at a tuner, you'll see it's labeled with KHZ on the AM side and MHZ for the FM. That stands for kilohertz and megahertz. Hertz is the unit of measurement we use for frequency. 1 vibration per second is 1 hertz, 2 vibrations per second is 2 hertz. But radio waves have a much higher frequency than that, so we measure them in kilo and mega. Kilo is times 1,000, mega is times 1,000,000. 940 on the AM dial means the waves are arriving 940,000 times per second. 95 on the FM dial means the waves are arriving 95 million times per second. It's a lot of waves. The frequency of these waves here are obviously much slower than that. 1 crest every 5 seconds is 1/5 hertz. Here's how frequency and a radio work. This tuning fork here is the note middle C. It has a frequency of 262 hertz. This tuning fork is the note A and has a frequency of 440 hertz. If I ring the A tuning fork and hold it up against the C, nada, nothing happens. But if I were to happen to have another C tuning fork, 262 hertz, and I ring it, the waves from one tuning fork are ringing the other because they're on the same frequency. Your radio antenna, it works the same way. Pretty cool, huh? What about staying in shape for surfing? I mean, do you do specific exercises? Is it cardiovascular? Is it weightlifting?
Right now I'm running and swimming and, trying to keep loose, and so I'm doing my yoga. At different times when I'm trying to actually strengthen, I'll lift weights on my legs, and when I'm trying to improve my surfing techniques, I'll get on the big Swiss balls and stand on them and have medicine balls thrown at me and do balancing things. And, it's nice to have variety, and it's great to have, like, purpose in where you're trying to go with advancement.
You can actually see waves using a telephone cord like this. Now, if Mara sends one pulse down this way, it reflects and comes back. If she sends 2 pulses, they reflect, return to the same place. And if she continues to send pulses, it'll form a pattern that looks like this. But what's the difference between this wave and waves in the ocean?
The waves at the beach are moving and all the bits of water move. This one has places where it stays stationary. The wave moves back and forth.
Right, we call that a standing wave, but how come it doesn't move?
The energy she's putting through the cord goes through the cord but has nowhere to go, so it reflects back.
Okay, so a standing wave actually results from 2 waves traveling in opposite directions, right?
Right, that's what makes a standing wave.
Waves at the beach are more typical. Most waves are traveling waves, and they move from one place to another.
Right, so the water is moving towards the shore.
The water's moving up and down, and the waves are moving through it, but not actually towards the beach. The water stays in the same place.
No way.
Way.
You mean to tell me the water's not moving towards the beach?
Only after the wave breaks, then the water moves up the beach.
So what's up with that?
If we put a mark on the cord, you can see what happens.
Okay? Watch when we make the wave. The tape moves up and down, but it doesn't move along with the wave.
Well, maybe that's because it's a standing wave, right? I mean, the waves out in the ocean are traveling, so the water must travel.
No, it's the same for waves in the water. We're proving it right now. As the waves pass, we just go up and down, but we're not moving towards the beach.
So the water transmits the energy without transmitting matter.
Right, and it transmits it through the medium of water.
Medium? What's a medium? You see, the thing with sound waves or water waves is that they move through a medium, but they don't move the medium. When you hear a sound, like radio from a speaker, the sound waves are traveling out through the medium of air. Now, if the air moved every time you heard a sound, you'd feel a wind, but you don't. If I eat a piece of this garlic, start talking to my friends here, hey guys, how's it going? It's not a problem when they hear my voice, but when the air from my mouth reaches them,
One thing you haven't said is that sound travels in different types of waves than water.
What do you mean?
Well, waves on the beach are what's called transverse waves, and sound travels through longitudinal waves.
so what kind of wave is this?
This is called a transverse wave because the wave motion is at a right angle to the direction of the wave speed.
So the wave direction moves this way, but the crest and the trough move in this direction.
Right. Most waves are transverse. The waves on the water, the waves on the strings of musical instruments, even light waves and radio waves are transverse.
But some waves, like sound, travel differently.
Sound travels in a longitudinal wave, also called a compression wave. The air particles move in the same direction as the wave. It looks like this.
But where are the crests?
Instead of crests, we have compressions. See the compressed areas. And instead of troughs, there's the area between compressions, called rarefaction.
Okay, so when you're measuring a longitudinal wave, you have to measure from compression to compression instead of from crest to crest?
Right.
If we use arrows to show how much and which way each particle is displaced as the compression wave passes through them, we get a graph that looks like this. If you were to take all those arrows and turn them vertically, the shape now makes a sine curve. That's what oscilloscopes do. They convert the compressions and rarefactions so we see them as sine waves. Okay, so we've seen that waves are measured in amplitude, wavelength, and frequency. And if we use wavelength and frequency, we can figure out something else about a wave. Its speed.
It's actually pretty easy to figure out a wave's speed if you know the frequency and the wavelength. So we can use the equation speed equals wavelength times frequency.
Okay, well, we figured out that these waves here have a wavelength of about 5 meters, and a crest passes every 5 seconds, right? So our frequency is 1/5 hertz. So we just plug in our numbers. Wavelength is 5 meters, frequency is 1/5. 5 times 1/5 is...
1 meter per second.
Oh, wait a second, that's only 2 miles per hour.
Well, these are just baby waves. Big waves can travel as fast as hundreds of miles per hour. Sound waves travel at about 350 meters per second at sea level. And light travels almost 1 million times as fast at 300 million meters per second.
Wow. Imagine if you could surf a light wave.
That would be pretty cool.
Okay, guys, so what did we learn?
Waves are energy moving through a medium, like sound waves through air.
Energy is transferred without matter being transferred. The water moves up and down but doesn't get closer to the beach.
Waves are measured in amplitude, wavelength, and frequency.
There are transverse waves like light and longitudinal waves like sound. And to find the speed of a wave, just multiply the frequency times the wavelength.
Okay, cool. That's it. I'd like to thank Rochelle Ballard. Right. And our students, Ferris, Melissa, Ryan, and Ryan, for helping us out today on ESPN Sports Figures Making Waves. I gotta go. Gonna catch some energy.